be seeing about the first part of Special Theory of Relativity, what led to the development of Special Theory of Relativity. Hope this makes your idea or understanding of Special Theory of Relativity a bit more clearer. So without any further ado, let's get right into the video. Now, whose idea was this genius idea of developing the special theory of relativity and the general theory of relativity? Yes, it was none other than Sir Albert Einstein. Albert Einstein is one of the most celebrated scientists of the 20th century. Widely regarded as the father of modern physics, he was born to Hermann Einstein, an engineer and a salesman, and Pauline Kokon, both non-observant Jews, on 14th of March 1879 in Ulm, Germany. Einstein settled in Switzerland and then relocated to the United States after Hitler's rise to power. Now, we could say that Einstein's theories on relativity, which are the special theory of relativity and the general theory of relativity, has laid the foundation for an entirely new branch of physics, the shift from classical physics to quantum mechanics, preceded via Sir Albert Einstein's developing the general theory of relativity. So, aren't you curious to know more about it? Let's jump right into it. Now, what led to the development of special theory of relativity? Broadly speaking, we could classify this as due to three main reasons, which are the inadequacy of Galilean transformation equations, which showed that up until then, everyone believed that if the frame of reference is changed, it doesn't mean that the time is changing. They viewed time as a constant and formulated the equations, transformation equations. But then came the Lorentz transformation equations, which proved that time is the suspect. Time may not be constant. So we got an entirely new transformation equations with Lorentz transformation equations. And what's it all Michelson-Morley play here? Michelson-Morley showed or debunked the existence of a very famous hypothesis in those times, that is, the presence of a constant universal reference frame called the ether. Michelson-Morley's experiments completely debunked this notion of ether and proved that there is no such medium as ether. All these are connected together in the two postulates of the special theory of relativity by Sir Albert Einstein in his 1905 paper on the electrodynamics of moving bodies. In this video, we are going to explore more about the Galilean transformation and why it was inadequate. So let's jump into Galilean transformation. Galilean transformation. Imagine you are in a railway station watching a train pass by with a constant velocity v. Do you think both of you are in the same frame of reference? In physics, a Galilean transformation is used to transform between the coordinates of two reference frames which differ only by constant relative motion within the constructs of Newtonian physics. Now consider the previous scenario wherein we saw a girl observing a moving train with constant velocity v from a platform. Obviously, the girl was in a fixed frame of reference while the train was in a moving frame of reference with constant velocity v. In such a scenario, if we are to observe a bottle, a water bottle, which is next to a passenger in the train, at time t equal to 0, both you and the water bottle and the passenger are at rest because there is no motion. But as soon as the train starts to move, the passenger and the water bottle next to him will start to move away from you. Now suppose x, y, and z are the coordinate systems of your frame of reference, and x dash, y dash, and z dash are supposed to be the passenger's coordinate systems from the moving frame. Now, if you want To locate the water bottle, you will locate it using x, y, z coordinates. What about the passenger? He would have to locate the water bottle next to him using x dash, y dash, and z dash coordinates. Now here comes the play of classical mechanics and Galilean transformation equations. Both x and x dash are not equal, and this is given by x dash is equal to x minus yt, y dash equal to y, z dash equal to z, and t dash equal to t. These equations are known as the Galilean transformation equations. Now, why does this happen? Because at time t equal to 0, both of you are at rest. Both you and the train and the passenger in the water bottle inside the train at t equal to 0 are at rest. But as soon as the time starts running, as soon as the train starts moving, the water bottle along with the passenger will start to move away from you. And thus the position or the coordinates of the water bottle will start to change. But what about the passenger who's next to the water bottle, who is inside the moving frame? With respect to the passenger, the water bottle is at rest. So if we calculate the x, y, z coordinates of the water bottle from you, and if the passenger is calculating the same x dash, y dash, z dash coordinates of the water bottle, both would be obviously different. That's how we get this Galilean transformation equations, which are a direct consequence of the classical mechanics from Newtonian laws. Remember, Galilean transformations are based on two assumptions. First one, there exists a universal time t, which is the same in all reference systems. Two, the distance between 2 points in various inertial systems is the same. Now, here lies the basic inadequacy of Galilean transformation. The equations below are only physically valid in a Newtonian framework and not applicable to coordinate systems moving relative to each other at speeds approaching the speed of light. Here comes the need of another set of transformation equations to describe the motion, and that is the Lorentz transformation equations. We will be covering the Lorentz transformation equations in the next part of the video. Stay tuned for the next video.